Hello everyone, my name is Ziqing Ou, a PhD student at Imperial College London. I am very glad to introduce our paper, Learning Neural Set Functions under the Optimal Subset Oracle. This work is done when I interned at Tencent AI Lab. Firstly, I will give some backgrounds of set function learning. Imagine you are buying some products. For everyone, you have a set function, say utility function in your heart, which takes the subset of products as input and output a neural value. You might buy the subset of products which maximize the utility function. There exists another application that has the same data generation process. For example, in anomaly detection shown in the left, you want to detect the male images from a bunch of females. In this case, we could explicitly write out the underlying utility functions, which is the sum of difference between two indicator functions. It can be seen that the subset of male images maximize this set function. Another example is compound selection. You want to select a subset of compounds that satisfy some desirable properties. In this case, the selected subset of compounds can be viewed as maximizing some underlying set function. However, unlike set anomaly detection we saw in the left, you can explicitly write out the set function in this case. Here is the setting of the set function learning. We assume we can assess the oracle utility function of a subset, which is impossible in real-world applications. Instead, the training dataset is given in the form of pairwise of ground set and the corresponding optimal subset. The goal of set function learning is to learn a surrogate set function f theta to approximate the oracle utility function f theta star. That's to say, we want to find a parameter theta in the hypothesis space such that the optimal subset oracle maximizes the set function value. In this paper, we relax this problem in the maximum likelihood principle. We require the set probability is proportional to the set function, such that the optimal subset oracle maximizes the probability which is required by the assumption of set function learning. However, the question is how to construct a probability for a set. Here are some desiderata, permutation invariance, and variant ground set, which are naturally required by the set function. We resort to the energy-based model, which takes the set function as negative energy function. Moreover, to satisfy the desiderata, we apply deep set architecture to model the set function, which satisfies permutation invariance and variant ground set. To change the energy-based model, we use marginal-based loss. Specifically, we minimize the Cal divergence between the variational distribution and the energy-based models. We specify the variational distribution as a multivariate binary, and each dimension stands for the probability that the corresponding element is in the optimal subset. Note that by using the mean field variational inference, the optimal variational parameter psi is differentiable with respect to the parameter of the energy-based model. Therefore, we could change parameter theta by differentiating through psi star using cross-entropy loss. To summarize, we loop these two steps for multiple iterations. In each iteration, we first fold variational distribution Q to catch up with the model P by mean field inference. Then, we push the model P to the data distribution using cross-entropy under the guidance of the surrogate distribution Q. Here is the overview of framework. Equip set. We amortize the variational distribution as a neural network, which takes a ground set as input and output the variational parameters, this made the training procedure more scalable. After training, the optimal subset could be sampled by rounding the variational parameter psi. We evaluate equip set in three applications: product recommendation, set anomaly detection, and compound selection. Equip set achieves shorter results on all these three tasks. Specifically, in the product recommendation, equip set improves 33% on average compared with the baselines. Please refer to our paper for more results and details. We have released the code. Please check it out. Thanks for your listening.